Okay, so thank you all for coming here and attending this last session of the reading group. I'm Emma Caizergues. I'm an intern in Nokia Bell Labs, supervised by François Durand and Elie de Panafieux. And today I'm going to talk about a generating function, and I'm going to do an introduction to generating functions and to introduce you to a combinatorial technique, which is called inversion technique. So what I'm going to do is that I'm first going to give you some theory on generating function and how they work. Then I'm going to briefly give you the idea of the inversion technique. And then I'm going to apply this technique to a special case, which is counting bipartite graphs with degree constraint. And then I'm going to do a small conclusion. So let's start. First, we need to define what we mean by counting something and enumerating something. And we are going to do it on a special example. So we are considering a combinatorial class C. And a combinatorial class is just a special type of objects. And for this example, we are going to count simple graphs, simple unlabeled graphs. And here you see that there are only labels on the vertices and no labels on the edges, and that's important. Okay, so what we mean by counting this object is that we just want an expression for this quantity. So we want to know how many graphs of graphs with n vertices and m edges there are. And so in order to find this quantity, one thing we can do is just describing this object, how we construct, how we build such an object. Well, first, we add some vertices with some labels. Here, for example, let's say that we have 4 vertices, and then we need to add the edges. We have all these possible locations for the edges, and note that as it's a simple graph, we do not allow multiple edges. So it makes a total of 4 choose 2 possible location for the edges. And then let's imagine that we want to place, for example, 3 edges. Then the number of possibilities we have for these 3 edges is 4 choose 2, choose 3. And here we took the special case where n is equal to 4 and m is equal to 3, but we can just generalize this case and obtain the formula for C and M. So here you can see that by just describing how the object look, we can come with the formula. But sometimes it's not that simple, and we need to build tools that are going to help us to count these quantities. And one of these tools is generating function. The generating function, the idea of it is that we are going to attach a variable to every particle of the object. So in our case, we are going to attach a variable to vertices, which is Z, and one to the edges, which is W. And then we are going to define this function. So this function is the sum for every graph in the class of Z to the power of n divided by n factorial times W to the power of m. These n of g and m of g are respectively the number of vertices of the graph G and the number of edges of the graph G. Okay, so we have this formula, and written like this, it's not obvious how it's going to help us to find the quantity C and M, but we can rewrite this sum as this sum. And here you can see that now we have a sum on N, M, which are parameters, and we have this quantity right here, C and M. And one thing that I have not mentioned is that here we have divided by n factorial and not here. And it's just because in our case, the vertices counted by z are labeled and the edges are not labeled. And we will see later why we divide here by n factorial and when it's labeled and not here. But for the moment, let's assume that we have this formula, okay? And now to find this quantity, we just need to extract the coefficient. So here I put a small notation for the extraction. So here, if we have a function that looks like this, we just say that this notation is for f of k. Okay, so we can see that if we arrive to find first the generating function without knowing this quantity, then we will be able to know this quantity by just extracting the coefficient. We are going to do this later, but for the moment, we need to define some operations that are going to help us build this quantity right here without knowing this. Okay, so let's talk about the operation. First, the addition. If we have a class C that is either an object of, that is either A or B, so this plus is just to symbolize the union, then the generating function is just going to be the sum of the both generating functions. And let's see why this is true on an example. Let's say that, for example, the class A is just nothing.
So, I have a question. Yeah? for the addition, C equal to A plus B. Does it mean that the graph will be unconnected? There is no connection between A and B, or because you say it's a union, so it's, for me it's not clear how you have two graphs.
Yeah.
So
these classes right here are not necessarily graphs. They are just combinatorial classes. And you can see that in the example, for example, I considered that A is the empty set and that B is just a single edge. Okay.
In fact, you don't add an object of class A and an object of class B. Just consider the whole set of objects that are either in class A or either in class B.
So you can see that here, the C with A plus B is just the disjoint union of classes.
So it's more clear now for me. But can A and B have common elements? Is it possible, or because they are always different?
They are always
disjoint union.
Yeah.
Disjoint union. Okay.
You can have objects of the same type in both classes. For example, I could have said that here I have an edge, and so I would have written E1 and E2 here.
For example, if A is empty set and B is empty set, then you have two empty sets, or two copies.
Yeah, two copies. But we will see later. There's an example where we have in A and B some same type of object.
If you take E equals to B, you got C equals to C. It's not possible.
No. Just,
okay, so we are going to define a variable. So here, remember that E is an edge, and so we are going to introduce W that counts the edges. And now we need to find the generating function of A and B. Well, A has only one object that has 0 edges. So A of W is equal to 1, which is 1 times W to the power of 0. B has one object in it that has one edge. So B of W is equal to W, 1 times W. And then C has one object with 0 edges and one object with one edge. And so C0 is 1, C1 is 1. And so C of W is 1 plus W, which is exactly A of W plus B of W. Okay, then we have a similar formula for multiplication. So then if C is the product of A and B, then the generating function is going to be the product too. And again, let's consider an example. So we have A that is either nothing or an edge, and B, either nothing or an edge. So you can see that here we have copies. I didn't put like 1 and 2 here because it's weird to do that, but they are just copies. And then C is this set right here. So either you choose nothing in A and nothing in B. So here you have nothing. Either you choose one edge, the edge in A and nothing in B, which is this drawing. Either nothing in A and an edge in B, which is here, or either you pick the 2 edges. And so you have C that is this set. Now for the generating function of A, you have A of W that is 1 plus W and B of W that is 1 plus W. That's what we saw before. And now C of W, if we do the same calculation, C of 0 is 1. There is only one object that has 0 edges. C of 1 is 2, which are these 2 objects. And C2 is 1, this object. And so we have this generating function for C. And you can see that if you multiply A by times B, you obtain here exactly the same formula. So the multiplication works too. If you iterate the multiplication and you get you try to get a K sequence, it's exactly the same. You will have, for example, if you have K times A here, you will have exactly the same formula. It's just by induction. Not gonna stay long on this slide, but just know that it works because here you have 1 plus W to the power of K, and it works exactly the same, and it works well. Okay, so that was for unlabeled structure. Now for labeled structure, you can see that it works too. So we have here exactly the same formulas that in the unlabeled case. And I just added this because it's going to be helpful later to have this operation. So if we have a set of A, then the generating function is the exponential of this set.
What does it mean, a set of B?
It's a set of elements of A.
It's power set.
It's power set of A.
Oh, okay.
2 to the power of A.
Okay, just to convince you that it works in the labeled case, I'm going to show you why the multiplication is true on an example. This time we say that A is either nothing or a vertex and B is either nothing or a vertex. So we are going to label the vertex. So C is this set. Either you take nothing, both in A and B, or you take an edge, a vertex in A, and you label it. So it corresponds to this object. Or you take this time an edge in a vertex in B, and you label it. And notice that we always start the labeling in A. So that's why here it's also labeled A. Or you take 2 vertices and label them A and B, or the other labeling that is possible, so B and A. And so if we say that Z counts the vertices, then A of Z is 1 plus Z, same for B. But this time, we are going to see that the factorial comes here because C1 is 1, it's this object. C0 is 1, C1 is 2, and C2 this time is 2. But here you can see that these 2 right here compensate. And so when we do the product, which is A times B, we can see here that we have indeed 1 and that it's well equal to C of Z. So that's the reason why when we are in the labeled case, we divide by this factorial. It's in order to ensure that these operations stay true. Okay, so now that we know the standard operation, we are going to try to find the generating function of simple graphs without calculating the quantities C and M. So here we put, as before, 4 vertices, and they are labeled. So this action right here corresponds to this variable right here, so z to the power of 4 divided by 4 factorial. Then, again, we have these locations that are possible, and in every location, we put either nothing or an edge. And so this corresponds to this generating function, either nothing or an edge. And we have, remember, 4 choose 2 possible locations. So we need to multiply this quantity by 1 plus w to the power of 4 choose 2. And so if we generalize this again to every number of vertices possible, we obtain this formula right here. So we just summed this quantity for every possible number of vertices. So we have this generating function. We are able to find this without calculating C and M. And then if we develop this with the binomial formula, we end up having this formula. And so what we did here, we found the generating function first. We calculated it, we did some calculations, and then if we extract the coefficient right here, we then have access to C and M. Okay, so that was for a bit of theory on generating functions and why they are useful. And now that we know how to manipulate this generating function, we are going to be able to describe the inversion technique and to apply it. So
sorry, just a question. I do not remember, you said at the beginning, but why do you have 1 plus w? I do not remember.
Okay, because here you either place nothing or an edge. Okay. Okay. So a brief explanation of the inversion technique. You have a combinatorial class A and a combinatorial class B. And imagine that you are able to give a generating function for this class, but you are not able to find one for this class easily. Then the inversion technique suggests that if you are able to transform an object of this class into an object of this class, then if you reverse this transformation right here, one technique to find this generating function is first to calculate this generating function, go into this edge, so transform it, and then you will have a generating function for this class. We are going to apply this technique later. Okay, so that's for the idea of the inversion technique. Now we are going to apply it to simple graphs with degree constraints. So our combinatorial class A is going to be bipartite simple graphs with degree constraint. I'm going to explain what it means to have degree constraint. So here you have a bipartite simple graph with left vertices right here and right vertices right here. And what it means to have degree constraint is that you want to attach to every one of these vertices a function, and every one of these vertices a function that is going to constrain the degrees. So here we are going to attach a function delta to these vertices and eta to these vertices. And so here you can see that this vertex has degree 2. So we are going to attach to this vertex delta 2. Same for this one. Here this vertex has degree 1, so delta 1. And same for the right vertices. And the idea behind this is that this delta and eta are just going to track the degrees of these vertices. And how it's going to constrain it is that we are going to add this quantity into the generating function of the graph. So let's take a look at the generating function. So let's y count the left vertices, z count the right vertices, and omega count the edges. Then we associate to the Bipartite class this generating function. So it's the sum for every graph in B of this quantity I'm going to talk about later and these variables. So you can see that we find again what we saw before with the simple graph with y to the power of p, z to the power of q, w to the power of m. And here again, p of g is the number of left vertices of g, q of g is the number of right vertices of g, and m of g is the number of edges. Okay, here is just the rewriting of this generating function, this time on sum with the sum on PQM. And so what is important here is this weight right here. By doing this, we will be able to constrain the degree. And how we do that is by giving particular definition for delta and eta. Let's do an example. If delta d is equal to 1 if the degree is either 0 or 1 and 0 otherwise, and eta is 1 if the degree is 2 or 0 otherwise, then you can see that this product right here is going to be 1 if and only if every left vertex has degree 0 or 1 and every right vertex has degree 2. And so in our sum right here, this product is going to be 1 either if and only if every degree is in the right degree sequence. And so that's how we can calculate the graph with degree constraints. Because when we are going to do the sum on every graph, this quantity will be strictly positive only if the degree respects the constraints. Okay, so we have this generating function, and we actually don't know how to calculate it immediately, but we can try to find another class that is going to be easier to count. And that's exactly what we are going to do now. And this class of graphs is weighted by bipartite multigraphs. So here you have a multigraph as before. And what has changed is just at first you can have now multiple edges and you have weight on the edges. Okay. And these weights here are just implicitly the same as multiplicity. So we think of this edge, for example, as actually two edges of multiplicity 1. And so by doing this, we are going to again attach delta and eta to the vertices, but this time note that here we attach delta 5 and not delta 3. It's because now we consider the degree of the vertices as the sum of the weights of the edges that are attached to it. Notice too that there are labels here. It's not really important, but it's just because it works well with the calculation, but we won't elaborate a lot of the labels here. What will just change is that in the generating function, we are going to divide by a factorial, but it doesn't change the idea of how we calculate this. Okay, so we have this type of object, and now we need to define the generating function. Again, y for the left vertices and z for the right vertices, but this time we introduce a vector w that counts the edges, which means this vector is indeed omega 1, omega 2, etc. And every omega k counts the edges of weight k. So here, for example, these 3 edges of weight 2 are going to be counted by omega 2. Okay, and then the generating function looks like this. So it's exactly the same as before, with here the products of the delta and eta. And here the only thing that has changed is that now we have a vector and we divide it by m factorial because we have labels. And I forgot actually here the factorial. Okay, so we have this generating function.
Just sorry to understand the notation. What does it mean, a vector to the power?
Oh, okay, yeah. It's the product for every k of omega k to the power nk.
Okay.
Okay, and this m factorial is the product of the mk factorial.
Okay.
Yeah, I didn't mention that, but yeah, good question. Okay, so now we are going to see how we can find this generating function. And actually, what we are going to do is just as the first case when you remember we counted simple graphs, we just described the object and the formula came, and that's exactly what we are going to do now. And we will obtain this great formula right here. It's not important to remember the formula. What will be really important is to understand how we construct this formula. So that's what we are going just after. So to prove this formula, I'm just going to place in the simpler case where we have no weights on the edges. So here we are going to consider the case where we have no weights, because actually it makes the calculation easier and the proof is just pretty exactly the same. The ID are the same, it's just easier. Well, it's not easier, it's the same, but it's just more pretty to count this. Okay, so we add a set of left vertices, okay, and these vertices are going to come with this generating function right here. We just take a set of left vertices, okay, and onto these left vertices we are going to attach a set of left half edges, okay. And you can see that here we need to track the degree of the vertices. And so we need to, here, we need to attach to y the contribution of these left vertices to the degree. And this comes to say that we attach to y this quantity right here. So it's the sum for every possible degree of delta d. So delta d will be the degree, d will be the degree of the vertex of this. And here it's just to say that u counts the number of left half vertices. So imagine that there are, I didn't put the label to not have a disgusting picture, but we have to imagine that there are labels here. And so, okay, so we attach left half vertices, left half edges that are counted by u, and this contribute to a degree, and then we just multiply y by this quantity right here. Okay, and now we do exactly the same with right vertices and we obtain a similar formula. Okay, and now what's left to do is to match the half edges here with the half edges here. And so, for example, this is a possible matching. And you notice that to be able to do this matching, we need to have the same number of half edges here and here, because otherwise we could not, there would be like a remaining half edge here, and we don't want that. And to enforce this number to be the same, we actually do this coefficient extraction. So that is just to say that every half edge here, we will have in total m half edges. And here we put the same m here so that we have the same number on the left and the right. Oops. And now we just need to show the contribution of these edges to the generating function. And that is just to say that we multiply by this quantity, because we have here and here m half edges. So we have in total m edges. And so the last thing we need to do is to sum on m, because here m is arbitrary. There is an arbitrary number of edges. And so we just do the sum on m. And here we have our generating function. So you can see that it pretty looks like the weighted case. And you can see that here it was easy to find in the way that we just described the object and it brought itself. Okay, so now for a small recap, we have our objects of type 3.
You said the half edges were labeled in this case.
Yeah.
So this means the edges we draw are labeled.
Yeah, the thing is, okay, you have labels here and labels here. And what you do when you match is that you're going to match the left edges with labeled 1 with the right edge with labeled 1. Okay, so imagine that here you have 1, 2, 3, and 4, and here 1, 2, 3, and 4. And so that's why we match this like this, is because we match 1 with 1, 2 with 2, etc.
So you've already done the match before you even draw them.
Yeah, actually, yeah.
Okay.
And you have several matches possible depending on the possible labeling here.
The match is defined by the label.
Yeah, the matching is defined by the label, and the label is arbitrary. So this is one example of a possible matching, and there are several examples. And that's why we multiply by this quantity and we divide by n factorial. It's just to symbolize that we have n factorial possible labelings. Okay. Okay, so now we have our generating function for B, and we need to define this edge right here. And again, I'm going to do it on an example on how I transform a graph here into a graph here. So let's take this simple graph here. And the first thing we need to do is to add weights on the edges, because the final object we want to obtain is a weighted graph. Okay, and now that we have this graph, what we are going to do is that we are going to transform every edge into a set of edges. Okay, so let's do that. First, take this edge. This edge is of weight 1. And remember, we want to track the degrees of the vertices. So we indeed have no possible choice. We just need to say that this edge remain the same, okay? Because if we transform it, for example, by 2 edges of weight 1, then the degrees will change here, and we don't want that. So we just have one possible choice for this edge. Now this edge. Here we have 2 possible choices. Either it stays the same, so an edge of weight 2, or we transform it into 2 edges of weight 1. Let's imagine that for this example, this edge stays the same. Then we need to take care of this edge, and let's imagine that, for example, this edge is transformed into 2 edges. So we will have this graph here with 2 edges here, and notice that indeed it does not change the degree here and here. And now we need to take care of this edge, and let's take, for example, this transformation. So this edge will be transformed into an edge of weight 2 and one of weight 1. Okay, then we have nearly what we want. We just need to add some labels into the edges. And that's it. We have indeed a multi-graph that has weights on the edges. So now we need to translate what we did on the graph into a generating function and into math operation. And so to do that, we need to say that we are going to consider this omega tilde k that counts the edges of weight k into weighted simple graphs, and omega k that counts the edges of weight k in weighted multigraphs. Okay, and the transformation we did before is just to say, sorry, that omega k tilde is just replaced by this quantity right here. So here you see an exponential that just corresponds to taking a set of edges of weight t. And here you see a coefficient extraction that just say, okay, all these half edges we are taking of this set, in total, I want a weight k of it. And that's just why we have this coefficient extraction. If you wonder why there is a -1 here, it's just because here the sum starts at 1. So that's why there's a -1, but it's not important. What really is important, actually, is that we are able to write omega k tilde as a function of omega, the vector omega. And so I'm not going to detail how we inverse this formula, but as we can write this as a function of omega, we will be able to write every omega as the function, the inversion function of the vector omega tilde. And so, yeah, this is the inversion we are able to do because it has a nice looking here. And so if we place this into the recap, we have our generating function, we have our operation here, and we are able to reverse it. And this just gives us this formula right here. It's not important to really look at what it looks like. It's just important that we are able to reverse this edge. And well, that's it. We are just going to replace now in this generating function every omega d by this quantity right here. And this will give us the generating function for simple graphs, which is here. Okay, so you can see that it pretty looks the same as the multigraph function. We still have this exponential right here, this coefficient extraction. And here you can see that we have omega to the power of something and -1, this -1 coming from here. So we have basically our formula.
For notation.
Yeah.
Sorry, the dot is multiplication.
It's scalar product here.
Okay.
Okay. And so we have this formula. And as a conclusion, I'm going to do 2 small remarks. The first remark is that when we look at this formula, it can seem quite complicated, right? We can wonder if we can compute it, like, is it easy to extract the coefficient on it, etc. And the thing is, even if this exact formula is complicated, what we can do is to do some analysis on it and to do some asymptotic analysis. And for example, if we make one of the parameters tends to infinity. And when we do that, very often we obtain very much more simpler formulas and very nicer formulas that we are able to really analyze and that we are able to see what they mean. Okay. And another remark is that here you can see that we sum on a vertex on a vector m, and this vector is a priori infinite. But if you remember well, what we want to do is to constrain the degree. And if the degrees are constrained, it means that we have a maximum degree. And if we have a maximum degree, then we have a maximum number of half edges right here. And so this m actually will be a finite vector. Okay, and the final remark is that here, if we compare the 2 structures we wanted to count, here we have simple graphs, which we wanted to count, and here we have multigraphs. And it could seem quite weird that we count this object easily because it looks more complicated, right? There are more stuff happening here. And the reason why it's simpler to count this object is that here, when we did the match, remember we did the matching, we don't care about having multiple edges. The only constraint of this on these half edges are to have the same number here and here. And actually, imposing that we do not have multiple edges is something that is complicated to do. And that's why it's easier to count multigraphs and to allow these multiple edges. And actually, this technique not only applies to bipartite graphs, but to graphs in general. And we are able to do the same inversion technique by counting multiple graphs onto not bipartite graphs. And so that's it. Here are the references, and if you have any questions, don't hesitate.
I have a question.
Yeah.
Can you elaborate more about matching and its relationship with convolution? Because in my opinion, it's kind of convolution, and you turn this into a generating function like map a combinatorial problem into a spectrum domain, and the matching turns the convolution into the product of generating function, and you define the relationship.
You're talking about this,
Yes,
right?
yes. The left hand side and right hand side are two functionals that's connected by convolution, I think.
I don't understand your question.
Okay, maybe it's another.
I don't understand what you mean by convolution.
By convolution, I mean because the edges, the connected edges are constant, because the left hand set must match the right hand side.
Yeah.
And then the combinatorial in left hand side and the combinatorial in the right hand side can be independent. Right.
They can't be independent because at the end you want the same number here and
the
here.
same number is defined by the convolution, the constant convolution kernel. Okay, maybe we can discuss later.
Yeah.
Because it's
Other questions?
Can you just go back to the part where you go from simple graph unweighted to weighted?
Yeah. Okay, so it must be here.
Say you just add weights.
Yeah.
Arbitrarily, and that works.
Yeah.
Okay.
Well, what I hide here is that okay. I hide something. Okay, so you do that, then you do that, and here, if you notice, this transformation is between weighted simple graphs and weighted multigraphs, and so you apply this transformation, but here the omega tilde actually will be a special vector, and this special vector will be omega and 0, 0, 0, 0. Why? Because here it's just to say that here having no weights here just means that every edge is of weight 1. Okay, and so we are going to apply the inversion to this special vector to say, okay, now every weight.
So you're not adding weights, you're generalizing.
Yeah, and then restricting.
Okay.
Yeah.
That makes sense.
And if I may add something, the reason why we need the weights is because we cannot otherwise solve this system if we don't have enough variables on the other side. So
you need the weights for the multigraph. Well, you need the multigraph, so you need the weights to be able to solve it. I just didn't understand why you were adding weights on the